today's tape, I'm going to give you two more applications of determinants. In the first application, I'm going to give you a mathematical formula that can be used to calculate the inverse of a matrix. Now, you will probably not want to use the formula if you're going to have to calculate the inverses by hand. The row reduction method that we discussed previously is still the best way of calculating the inverse of a matrix. But the formula is very good for notation and for computer use. In the second example, I'm going to show you how to solve systems of equations using Cramer's rule. Now, most of you have used Cramer before. You can solve systems of equations with determinants by using the rule. Let A be a square matrix. The matrix of cofactors, C, is the matrix that you can see here. C11, C12, C13, and so forth. Well, Cij, remember, is going to be -1 to the I plus j Mij, where Mij is the minor. Mij is the determinant with row I, column J deleted. So you start with the matrix A, and each element in A, each Ij, has a cofactor Cij defined by this formula. The adjoint of A, noted ADJA, is the transpose of the cofactor matrix. So to find the adjoint, first of all you have to find the cofactor matrix and then take its transpose. So the adjoint of A is the transpose of the cofactor matrix. Now, if A is invertible, that means if it's not singular, then A inverse is equal to 1 over the determinant of A times the adjoint of A. So this is a mathematical formula that you can use to calculate the inverse of A. 1 over the determinant of A times the adjoint of A. Let's do an example in which we find the adjoint and inverse of 1, 2, 3, 0, 1, -1, 2, 2, 2. Well, the first step in the process is to get the cofactor matrix. So the first step will be to get the cofactor matrix. Well, C of 1, 1 is going to equal to a -1 to the 1 plus 1 times the determinant with row 1 and column 1 removed. So that leaves us with 1, -1, 2, 2. Now -1 to the 1 plus 1 would be -1 squared, which is positive. And then the determinant, that would be 2 minus a -2, which would be 4. So C11 is equal to 4. C12 Now that's going to be negative 1 to the third. 1 plus 2, so that's going to be a negative. And the determinant with row 1, column 2 removed is going to be 0, negative 1, 2, 2. Zero times 2 is 0 minus a negative 2, so that's going to be a 2, but taking the inverse of 2, I'll get negative 2. So C12 is negative 2. C13. Now that's going to be a negative 1 to the fourth, so that would be a positive. And we have the determinant with row 1, column 3 deleted. So I would have 0, 1, 2, 2. 0 times 2 is 0, minus 2 would be a negative 2. C of 2, 1. 2 plus 1 is 3. Negative 1 cubed is negative, so it's going to be a negative. And take out row 2, column 1. So I have 2, 3, 2, 2. Four minus 6 is negative 2, but the opposite of negative 2 is positive 2. Now we do C of 2, 2. 2 plus 2 is 4. Negative 1 to the fourth is positive. And if I take out row 2, column 2, I'll have 1, 3, 2, 2. 2 minus 6 is negative 4. C of 2, 3. The sign is going to be negative because 2 plus 3 is 5. Negative 1 to the fifth is negative 1. And I take out row 2, column 3. I have 1, 2, 2, 2. Two minus 4 is negative 2, but the opposite of negative 2 is 2. C of 3, 1. Sign is going to be positive. 3 plus 1 is 4. Negative 1 to the fourth is positive 1. Now take out row 3, column 1. So I'm left with 2, 3, 1, negative 1. There'll be a negative 2 minus 3 is negative 5. C of 3, 2 is going to be a negative. And because 3 plus 2 is 5, negative 1 to the fifth is negative 1. I take out row 3, column 2. So if I take out row 3, column 2, I'm left with 1, 3, 0, negative 1. Well, that's going to be 1, negative 1, minus 0, which is negative 1. So the opposite of negative 1 is 1. And finally, we'll do C of 3, 3. Well, it's going to be a positive, and the determinant, if I take out row 3, column 3, I have 1, 2, 0, 1. That's going to be 1 minus 2 minus 0, which is 1. 1 minus 0 is 1, and be a positive 1. Now putting all the numbers together into the cofactor matrix C, we have C of 1, 1 is 4, C of 1, 2 is negative 2. C of 1, 3 is negative 2. C of 2, 1 is 2. C of 2, 2 is negative 4. C of 2, 3 is 2. C of 3, 1 is negative 5. C of 3, 2 is 1. C of 3, 3 is 1. So the adjoint of A is equal to C transpose, which will be C with the rows and columns interchanged. So it would be 4, negative 2, negative 2. Take the row, make it the first column. 2, negative 4, 2, negative 5, 1, 1. So here is the adjoint of A. Now we know that A inverse is 1 over the determinant of A times the adjoint of A. So to finish my calculations, I need to do the determinant of A. Well, we'll go back to A, which is 1, 2, 3, 0, 1, negative 1, 2, 2, 2. And we want to get the determinant. Now I could do some row operations to reduce it, but what I think I'll do is just expand around the second row. It won't take very long. So I don't have to worry about 0 times anything is 0. So I'll go to 1 and multiply 1 times its cofactor. So it's going to be a negative 1. That's 2 plus 2, so that would be negative 1 to the 4th times the determinant with row 2, column 2 left, so that would be 1, 3, 2, 2. Plus a negative 1 times its cofactor. Now that's going to be a negative 1 to the odd power, be 3 plus 2, so it's going to be a negative 1, times the determinant with row 2, column 3 gone. So that's 1, 2, 2, 2. Now this is a positive for the negative 1 to the 4th, so it would be 2 minus 6 is negative 4. Now negative times negative is positive, so it would be 2 minus 4 is negative 2, which is negative 6. So the determinant of A is negative 6. So A inverse is going to be 1 over negative 6 times the adjoint, which is 4, 2, negative 5, negative 2, negative 4, 1, negative 2, 2, 1. So A inverse is going to be a negative 2/3, a negative 1/3, a positive 5/6, a positive 1/3, a positive 2/3, a negative 1/6, a positive 1/3, a negative 1/3, a negative 1/6. Okay, now let's look at Cramer's rule. If a system of n linear equations has an invertible coefficient matrix A, then the solution to the system is given by x1 is equal to a1 divided by a, x1 is equal to the determinant of a1 divided by the determinant of a, x2 is equal to the determinant of a2 divided by the determinant of a, and so forth out to x to the n is equal to the determinant of an divided by the determinant of a. Now A is simply the coefficient matrix. Now A1 is the coefficient matrix with column 1 replaced by the constants. A2 is the coefficient matrix with column 2 replaced by the constants. AN is the coefficient matrix with column n replaced by the constant. So I wrote that for you here, where the ith column of AI is the column of constants in the system of equations. Let's solve 14x1 minus 21x2 minus 7x3 is equal to a negative 21. 4x1 plus 2x2 minus 2x3 is equal to 2. 56x1 minus 21x2 plus 7x3 is equal to 7. Now if we were going to do this by hand, we would be doing a lot of reducing before we started. But if I'm going to use the computer, and I am, to do the heavy work, I'm not that concerned with the large numbers. So what I'm going to do is just identify the matrices. A are the determinants. So the determinant of A is going to be just the determinant of the coefficient matrix. That's going to be 14, negative 21, negative 7, negative 4, 2, negative 2, 56, negative 21, and 7. So that's what A is. Now A1, the determinant of A1 is going to be the coefficient matrix replaced by, with column 1 of the coefficient matrix replaced by the constants. So in place of column 1, I put the constants. And I leave everything else the same. Now for the A2 determinant, that's going to be the determinant of the coefficient matrix with column 2 replaced by the constants. So I put the constants in column 2, and I'll leave column 1 and column 3 the same as for A. The determinant of A3 is going to be the coefficient matrix with column 3 replaced with the constants. Column 3 replaced with the constants. columns 1 and 2 would be the same as for A from your coefficient matrix. So then we know that x1 is going to be the determinant of A1 divided by the determinant of A. So all I have to do is to calculate the determinant of A1, calculate the determinant of A, and divide. X2 is going to be the determinant of A2 divided by the determinant of A, and X3 will be the determinant of A3 divided by the determinant of A. Now, rather than doing all those determinants by hand, I'm going to let derive do it. So I go to derive and I author my 4 matrices. So here is A, 14, negative 21, negative 7, negative 4, 2, negative 2, 56, negative 21, 7. Here we have A1. And check your notes that we just finished. Negative 21, negative 21, negative 7, 2, 2, negative 2, 7, negative 21, 7. Here we have A2. 14, negative 21, negative 7, negative 4, 2, negative 2, 56, 7, and 7. And finally we have A3. 14, negative 21, negative 21, negative 4, 2, 2, 56, negative 21, 7. Now to find x1, I simply author determinant. Now what I actually authored for step 5 here, I'll show you what I went to expressions. I went to author expression, and I put determinant, parentheses. Now for x1, it would be A1 divided by A, so parentheses number 2. Divided by determinant, parentheses number 1. Because see, expression 2 is the A1 matrix, expression 1 is the A matrix. So x1 is the determinant of A2 divided by the determinant of A. And that's what I have. Determinant of A1 divided by determinant of A. And I tell it to give me the answer. So it tells me that x1 is 1. Then I author the determinant of A2 divided by the determinant of A. And it tells me that x2 is 2. And then I do the determinant of A3 divided by the determinant of A. And over on the next page, it tells me that x3 is negative 1. Now, of course, from this step, I had to hit simplify to get to the answer. Simplify basic, just like we normally use with derive. So once you set it up with Cramer's rule, most any calculator or computer can quickly evaluate the determinants and give you the answer.